Good evening, everyone. So let's start with week 11. First of all, giving my introduction, I am Prableen Kukreja, working as a PMRF scholar in IIT Tirupati. So let's continue with the week 11 session. Just wait a second. I hope the screen is being shared. So last time we did with the QOS thing, that is quality of service. That is what we have done. We completed with IPv4, IPv6. Then we started with the QoS thing, and today we'll continue with the QoS. And we did about like what are the parameters which affect the quality of the service, which includes bandwidth, jitter, and delay, as well as loss, packet loss. And we did all these things in detail. What is jitter? What is delay? What is propagation delay? What is transmission delay, and all. And then we did the classes based on QoS, basic QoS architecture, admission control, classification, policing, and markdown scheduling, traffic shaping, traffic policing, and all the difference between them. Then we did the two algorithms, that is token bucket as well as leaky bucket algorithm, and the differences between them. I hope so. These things were clear. Today, let's wait for 2-3 more seconds. So now let's proceed. Today we'll complete the QoS thing. The routing part, as well as we'll do the MCQs on the SDN software. Am I audible? Thank you. So today we'll complete this SDN QoS part routing thing, and then we'll do the MCQs with the remaining SDN and routing part. And then in the next lecture, we'll complete with the data link layer. And one more thing that I have asked for the extra lecture as well, which is on Friday. Have you received any mail regarding that? Though I haven't also received the mail regarding the acceptance of that or something. I hope so. It will be on Friday, most probably 6 to 8. 2 hours lecture again. I've asked for the extra class so that your syllabus should be completed. And the next Tuesday, we'll have the revision lecture for that. Have you received any mail regarding that Friday? Can you write in the chat or unmute yourself? Let's proceed. I don't know why today only 1 or 2 people have joined. Otherwise, more than 20 always used to join. Okay. So as I have discussed in the previous lecture about the QoS parameters and all, and the basic QoS architecture and all, and today we'll discuss about the scheduling part. First of all, what does scheduling mean? If I talk about scheduling only, what does it mean? It means that maybe with the name scheduling, it means that maybe we are giving a higher priority to one packet and the lesser priority to the other packet. And why is it so? Because sometimes, like we have seen the classes like VoIP, like voice over IP, that is WhatsApp call and all. I mean to say voice call using internet connection, and the others are like file transfer protocol and all. So we have basically divided into classes. That is what we saw in the last lecture. So some are high priority and some are low, given low priority. Like class one, this is high priority VoIP, or is a class which is basically given the highest priority. That this is basically this service should be done first, because obviously file transfer can be delayed, but voice over IP, this is real time service, it cannot be delayed. So scheduling, in scheduling we have to give it as a priority, we have to give it on priority basis. That is our main motive of this scheduling part. Now if I talk about user level thing, now it may be like in the coming future it may be the thing, or maybe nowadays also, like if a network service provider is there, like we can tell the network service provider that I am using these kind of services, like I'm using the Zoom call daily and everything daily. Nowadays it's pretty common though, but earlier it wasn't that common, I'll say. So according to our plans, according to our requirements, we usually purchase our Wi-Fi pack and all. That is what, our data pack and all. If you need more data, we purchase more data pack and all. And if I talk about this class scheduling again, I'll say we have high priority packets, medium priority. Now only we discussed, and the low priority packet. Now the scheduler task. What is the use of the scheduler? Scheduler will basically first serve the high priority one, then the medium priority when high priority queue is empty, and then the low priority. Now we have two types of scheduling. One is preemptive, another is non-preemptive scheduling. Any idea what is preemptive scheduling and what is non-preemptive scheduling? Yes, class. Any idea about that? So, if I talk about primitive, though it may be in your OS as well, you might have done an operating system as well. What is primitive scheduling and non-primitive scheduling? If I talk about primitive scheduling, it's like suppose it serves first, obviously, not suppose, it will serve first high priority packets. Whatever it is in high priority queue. Then it will come to medium priority queue. That is what we discussed now only. Like first high priority, then medium priority. But suppose by the time it is serving this medium priority queue, some packets arrive again in high priority. Like okay, I'm serving it is serving the high priority one, but at the same time there are some packets arrived at that point. So what will now the scheduler do? Like it will prim this packet, it will go to the it will serve the high priority one, and then after that it will come again to the medium priority queue. So what does it mean that, like it will if I talk about low priority one, What can be the issue? Like, okay, it's fine. High priority means you have to deal them with the highest priority, and you have to if the packet arrives in the high priority queue, you have to deal with them. And when you are in the medium priority, according to preemptive scheduling, when something arrives in the high priority, stop that, first serve the high priority queue. What do you think? What can be the limitation in this primitive scheduling thing? Any idea? The limitation here is, okay, I served first high priority. Then I was serving medium priority, high priority packets again came. So then I served again the high priority. Then high priority queue was empty. I came to medium priority. Again, suppose high priority queue came, some packet came. Again, I'm serving. In this way, can I say that sometimes this low priority queue can go to starvation? The packets here may starve here. So yes, there is a limitation here. The low priority packets may starve sometimes there because we are busy in serving the high priority one. If I talk about advantages here in the primitive scheduling, obviously there is lesser delay for the packets in the higher schedule, higher priority queue as well as medium priority also, I can say. Now this is the primitive priority queuing, or I'll say primitive one. If I talk about non-primitive one is this is like, okay, first you serve high priority queue. Once high priority queue is empty, then go to medium priority queue. Now again, suppose high priority queue, the packets are there. It will not print from there. It will go to low priority. Then again, it will come to high priority one, turn by turn, round robin fashion. Now the next type of queuing is custom queuing. Is it clear? First of all, can you write in the chat? Is this priority queuing clear? Or are you having any doubt? Can you write in the chat? Yes. Yes, Vishwa, Naveen, is it clear? Clear. So now the next type of queuing is custom queuing. Now custom queuing means, here what does it we have here, we have different queues. Basically they have different sizes. So suppose one queue is having 20% of size, the other queue is having 30% of size, and the other one is having 50% of size. This is like this. So how it works? Basically, we have defined multiple queues here. Each queue, I'll say, is assigned maximum number of bytes or packets. Wait a second, I'll elaborate. Which means, suppose there is a limit, like how much, like I have written here 20, 30, or 50, or I'll say how many, like here, this queue, suppose high priority queue, it can have 1500 bytes. The other one can have 2000 bytes, can hold 2000 bytes of packet, and this one can hold, suppose, 1000 bytes of packet. This is suppose voice over IP, this is suppose video, and this is suppose file transfer. So each queue here is assigned the maximum number of bytes or packets. And here again, the router basically service the queue in round robin fashion. Round robin means first it will go to this queue, then this queue, then this queue, like pulse traffic up to this byte limit, like 1500 bytes up to this byte limit. It will pull up the packet and move to the next queue. In easy words, I have written in the layman language how it basically happens. Vedic, my voice is not audible. What about others? Naveen? What about others? Naveen, Vishwa, Shabana, SK? Am I audible to you guys? I think Vedic, can you check at your end? Because for others, it's fine, I think. Uh, you can disconnect and again connect your device. Maybe some connection, network issue in the network class. So it's basically custom queuing. First of all, each queue is assigned the maximum number of bytes. Serving each queue with like serving the router will serve each one with the maximum number of bytes and move to the next one. This is simple custom. Now coming to the next type of queuing, that is weighted fair queuing scheduling. So mainly, if I talk about the priority queue scheduling or those type of, that is, we may mostly call that as first level of scheduling. Once that is done, then we mostly comes to this weighted fair queue scheduling. We call it as second level of scheduling. Like suppose we have done we have served the packets on the basis of the priority. Now sometimes after that we are doing this weighted level of weighted fair queue scheduling. How is it done? Suppose here one packet is equal to 1 unit. Here one packet is equal to 4 units. Here one packet is equal to 2 units. And what do I want? That I want to ensure that fairness is there among every flow. I mean to say every flow will get equal amount of bandwidth. Every flow is getting the fairness. So how can I have the fairness? I can say that one packet of this one, basically one packet of this one should be transferred, 4 packets of this one should be transferred, and 2 packets of this one should be transferred. In this way, I can say 2 into 2, 4. Obviously, 4 cross, this is 4 and 1. So every, I'll say all of them are getting equal proportion of weight, because we are having different packets, different units of them. So that is why in order to assign them equal weight, we are doing this. Vedit, you can maybe again join it or join from other device or again join, because I think others can hear. And if someone else is also having the problem in audibility, please can you tell me in the chat? Inform me. So this is these are the type of basically the scheduling. Now coming to congestion avoidance. So what is our main motive? Our main motive is that one more thing in congestion avoidance, that high priority class shouldn't face this congestion at all. They shouldn't go to the congestion. Congestion may occur if the congestion has to be occurred. It's okay to be occurred in low priority class. We can deal it with congestion, like congestion control. Basically, we can deal with congestion avoidance like in TCP and all. But for the higher priority classes, the congestion control, like congestion shouldn't be there. This is our main motive. We have two types of traffic: elastic traffic. I'll come to this, how we'll relate it in elastic traffic. Elastic traffic is basically, it is increasing its rate or decreasing its rate based on the congestion. When there is no congestion, then obviously, like if I talk about AIMT, what we have done in TC, when there is no congestion, we increase the rate, the sender increase the rate of flow. And when there is congestion on detection, obviously, we reduce the flow. No congestion, increase the rate. If the congestion is there, detected, then reduce the rate. What can be the issue there? Any idea? What can be issue with this? If I'm increasing the rate and decreasing it, what can be the issue which we can face? This is a good idea, obviously, that if like elasticity in the traffic, if increase the rate or decrease the rate. But I think we have done in the last class about jitter, which means we don't want this jitter. We don't want, obviously, if I talk about this elastic traffic, it will introduce this jitter thing, which means we want a smooth or controlled constant bitrate traffic, not like going up or down, because it is not preferred for the real time applications. Because if you are watching it live, sometimes you are watching it like okay, live, and also like it's like you're watching very smoothly, then there is a buffer there, then there is again you're watching smoothly. You don't want this type of connection at all. So that's why like this elastic traffic sometimes introduces jitter, and for the real time applications it's not preferred at all, and inelastic traffic is preferred, in which you have smooth or control or constant bitrate traffic. So that is basically inelastic traffic. So, like sometimes we have the link where both the elastic traffic is also there and inelastic traffic is also there. In that case, there is an issue because in elastic traffic, obviously they'll increase the bandwidth, which can significantly, I'll say, which can significantly affect this inelastic traffic as well. Because inelastic, what does inelastic means? That we are going in the constant flow. Any doubt till now? Maybe am I too fast or is it going fine? Is it fine? So that's why we come up with random early detection. Any idea what does this random early detection means? Yes, class. Any idea about this? Come on. What about others? Yes, come on. Yes, yes. Why we came up with this random early detection? What does the name random early detection means? Can I say that, okay, what I said that, okay, I was having elastic traffic as well as inelastic traffic. Elastic traffic was like, okay, there can be increase in the rate as well as decrease in the rate of the flow. Why we are increasing the rate? When we are detecting that no congestion is there, then increase the rate. And if the congestion is there, then decrease it. If we are detecting it, as we have done in AIMD. Now, inelastic means like, okay, we are going with the constant bit rate. That is what, and when they are in the same flow, obviously, elastic traffic do affect this inelastic and there is a significant loss. Now, as the name suggests, random early detection. Okay, there is a, okay, congestion avoidance. Yes, packet scheduling. Okay. Aman, how congestion avoidance? Can you elaborate? How can you avoid this congestion with this random early detection?
I think we can drop packets that from certain applications which we think are sending too much packets and uh, congesting like the whole channel.
The main idea is basically we are basically dropping the packets if the congestion possibility is high, then drop the packets. As you are saying that, okay, if the sub application is basically congesting it lot, we are not basically allowing them. We are there is a threshold kept. Okay, this is the threshold, and if it is below the minimum threshold, then we are accepting it. And if it is between the minimum and maximum, basically, then we are like calculating the pack. Okay, I'll tell you. There is a, if suppose a packet is coming, we'll check the queue length. Is it average? Is it minimum? Like, please mute yourself if you don't have any doubt. So, if is it like crossing the max threshold, or is it crossing the min threshold? We have two types of thresholds, suppose. So, if it's like below the threshold, we are saying that it's average. It's fine for us. We'll accept the packet. And suppose if it's between min and max threshold, we'll calculate the packet drop probability. So, it depends on the class and all. We there is a whole the packet drop, whether the packet should be dropped or not, and like I'll come to that packet drop probability. And if it's like high probability, we'll drop the packet. Otherwise, we'll let it in queue. We'll it will be in the safer zone. If it's like low, I'll say it will be in the safe zone, which means it will in queue. It will enter the queue, and if it is high, I'll say that we'll drop the packet. And if the packet is more than the max threshold, then obviously we'll drop all the packets. If the queue is basically, oh sorry, if the queue is basically more than the max threshold, we'll drop the packets. So max this probability, there is a formula there that how to calculate this probability and all. I'll not go to those details. That is just a formula like how to calculate this. This is the main idea behind it. Again, going through what we have done, maybe because most of you have joined now only, because when I started the lecture, no one was there, I think. So, scheduling, we have done like primitive, priority based scheduling, primitive, non-primitive scheduling, primitive scheduling. Like obviously, you are in high priority queue. Once high priority, suppose some packets arrive, like you are in high priority queue, then once high priority queue is served, then we go to medium priority queue. And suppose you're serving this medium priority queue, at the same time the packets arrive in high priority queue, you stop there, print there, again go to high priority queue. Basically you are printing that. Basically you're stopping from one packet, again going to one queue, and again going to the other one to serve them. That is basically primitive scheduling. Non-primitive means you are serving whole high priority, then going to no medium priority, then going to low priority, then again high priority. You are not at all stopping there. If there is some packet in high priority, when you are serving medium priority, you will go on with the medium priority. That is non-primitive scheduling. I hope so. I'm not that fast. In primitive scheduling, there are limitations like starvation. In low, like suppose I'm serving medium priority, but some packet arrives in high priority, I go and serve the high priority. Again, I serve medium priority, then again the packet is there in low priority. Obviously, low priority one will go into the starvation. But for the high priority and medium priority, there is an advantage that there is less delay. Then we went to custom queuing. That is basically different queues are having different sizes, and how basically it works like each queue is assigned what maximum number of bytes we are giving each queue, and router will serve in round robin queue fashion basically, and it will pull the traffic up to this byte limit. Like suppose 1500, so it will pull the traffic up to 1500 bytes, then up to 2000 bytes, then up to 1000 bytes. Weighted fair queuing, most of times we say it as second level of queuing, basically to give equal weightage to everyone. Then we came to elastic traffic. In elastic traffic, now that is what we have discussed about. Now coming to integrated service architecture as well as differentiated service architecture. Basically, int serve and diff serve. Any idea about it? Yes, come on. Basically, if I talk about int serve, basically integrated service, I'll say these are the two types of architecture. Maybe I'm going like if I'm going too fast, please tell me. Just write in the chat. In serve architecture, basically we are here trying. It basically tries to provide guaranteed service. I'll say how it is trying to provide the guaranteed service. Again, the question arises. Like suppose, like service level agreement is there that all my packets it should reach within 10 milliseconds. So the network should ensure that it shouldn't take more than 10 milliseconds of delay. I'll say every router here should ensure in the route that okay, 10 milliseconds of delay, more than 10 milliseconds of the delay shouldn't be there. If I'll say that from the source to destination, whatever the service level agreement is there, we have to follow that. And every router should ensure about this SLA, which means that all the routers within the source and destination, all the routers here should coordinate with each other. To reserve the resources for this SLA, to guarantee this service, they should coordinate so that okay, like you should reserve this resources because we have to guarantee this service level agreement. Can someone tell me what is the issue then? Okay, we are here guaranteeing the service, okay, that there shouldn't be delay from source to destination more than this. Then what is the issue here? This architecture is good then. Yes, the issue here is like obviously there are so many ISPs router entire communication. It will become very complicated. Like obviously, if you are reserving the resources from all the routers, there can be source in one place and the destination in very far away place, and reserving all the routers, reserving all the resources in the routers. It's a huge tedious task. It's very complicated. That's why we came up with the second level. Though the second level, I'll say, don't give us the guarantee, but obviously this type of resource reservation, it is not, obviously it's not there. If I talk about a simple difference between int serve and div serve, obviously scalability means more, extending them more, extension like more routers and everything. Obviously that's very tedious task, like having more routers or covering more area, it's very tedious task. So obviously for int serve it's poor. For div serve it's good, though I'll come to that, because we don't have to do the resource reservation at all. Obviously here we have to do the resource reservation. Complexity, obviously it's high, whereas it's low there. Service guarantee, as I have said, that in InServe there is service guarantee, whereas here there is no strict service guarantee. So here basically we have a resource reservation protocol and all. I'll not go into much detail because we are not having that much of time. So we have here resource reservation protocol where we are basically reserving all the resources there. Whereas in DivServe, we have how does it behave? If I talk about DivServe, we have, suppose, I'll come to that. Suppose in DivServe, uh, suppose this is DivServe 1, DivServe 2, and DivServe 3. This is source. This is local ISP, suppose. This is tier 1 ISP. And this is also local ISP. And this is destination. Suppose my end-to-end delay is 30 milliseconds. And till the time I reach this DS2, it has already incurred 20 milliseconds of delay, suppose. So here, we don't require coordination among all the routers, I'll say. We need the coordination with this, I'll say, bandwidth broker. I'll come to this. So here DS3, suppose it will have the we'll have the agreement, the coordination with this. This will have the coordination among this div serve domains. Okay, it will ask the DS3 that okay, 20 milliseconds is already done. 10 milliseconds, is it possible to reach to the destination? It may happen DS3 don't agree because it's local ISP. It can happen. It can compromise the QoS. That is why we say that okay, we don't guarantee here the service level agreement. Guarantee is not there, but we do say that okay, we don't have to reserve the resources and all. That is the plus point here. And if I talk about bandwidth broker, basically it's an agent which is having the knowledge of all the organization priorities and policies and all. Now I hope so. This part, IntServ and DivServ, the main idea I have given to you about that. And if you'll face any doubts, we can cover the other things as well. Though the basic thing I have shared with you about this, what is DivServ and what is basically IntServ. IntServ is basically, and with this difference, maybe it's clear that okay, the service guarantee, obviously, it's not that strict in DivServ, whereas the service guarantee in IntServ is too strict, but the problem is the reservation there. Coming to the routing part. Any doubts till now? We are coming towards the next part of the lecture. QoS is completed. Now we are coming to the IP routing part. Any doubts till now? Should we proceed? So what is routing? Can I say we have several networks and routing is responsible for sending packets from one network to the another? That is what routing is. I'll try to cover today the whole routing. And I have come up with some examples also of the distance vector routing and link state routing as well, so that you can easily understand that. So if I talk about, first of all, as I think though we have done the addressing, hierarchical routing, hierarchical addressing and all, we know about that. Just I'll not skip at all that part. Just we'll go a little bit fast here. Like suppose here I have LAN 1. And here I have LAN 2, local area network 2. And here WAN. Basically routers and all. And what does in routing, what is there? There is a lookup table. We have to see the lookup table. Lookup table says, okay, where we have to forward the packet. And like, if I say about this, is it a feasible, like if I want to go from 1.1.2.3.4 to 1.2.3.5, is it easy or is it like how we'll maintain? Can anyone have like tell me about this? Just a that, yes, Sarah, the path of data packet travels. Okay, can someone tell me about this? How, what is the like limitation in this type of addressing scheme and all?
Limitation as in, ma'am?
Like if I want to go from 1.2.3.4, this is one LAN, and I want to go through, this is the LAN 2. How are these addressing schemes fine? Suppose this is the addressing scheme of LAN 1, whereas this is the addressing scheme of LAN 2. Is this fine? Is this hierarchical for LAN 1 and LAN 2?
If they are public IPs, then shouldn't they be in same subnet? And in that, and hierarchy is not there because
Hierarchy is not there.
it
So what
will,
is the limitation if the hierarchy is not there?
in that case, it will go the long way. So it will go from to the higher levels of IXP, NXP, all that things, and then it will go to LAN 2 to the very node route.
So, or in other words, I can say if I have a table here, I have to match with every entry, and obviously the routing lookup table will be very large here, because I'm not having the same prefixes. In other words, what does that mean? Hierarchy and all, they are the same starting prefixes are not there. If I'll come to that also, how we'll maintain the hierarchy and all. Maybe we have done we have done also there in the class full addressing how we are maintaining that, the same prefixes and all. Obviously here, if hierarchy is not maintained, then I'll say that router will go to each and every entry in the table. And obviously, if I have to add or delete or update anything, it is very tedious task, and it's a very large table. In other words, I can say, so that is why hierarchical addressing is important. Though I'll not go in that depth, as we have already covered about hierarchical addressing. That is basically classful addressing, the way we have done. Like the fixed number of prefixes, they are like 0001, how many, like fixed number of prefixes, the subnets and all. And suppose, what is the advantage behind that? Obviously, if the router knows how to reach to land, I'll give the example now, wait a second. Suppose this is land 1 and this is land 2. This is where, and this is my now my routing table is like, I think this notation and all we have already covered. You might know about this. Is everything clear? Should I proceed or should I explain you about this network mask and all?
No, no.
Mhm. So now suppose I have one more entry, that is this one more host is added. So it's easier to add new host, not required to change in the routing table, because we don't have to update every entry there. I only have to update this 567 5.6.7.0 slash 24. I like basically 5.6.7 star. I know how to reach there to the land 2. Rest is the which will contain from 5.6.7.1 to 5.6.7.2 for 54 it can contain. So if I'm adding the new host, if I want to go there, so it's very easy there. So that is what is the advantage of hierarchical addressing in the routing thing, rather than this flat addressing scheme, like with no hierarchy. That is what I was asking. What was the limitation there? The limitation is hierarchy is not there. Because the hierarchy was not there, it was obviously very large. And if I have to add something or delete something, update something, then also it's very tough. But here, if I'm adding a new host, it's very easy, because no requirement of changing in the routing table. So obviously there is a scalability through hierarchy, I'll say. Reduces the amount of updating and all. So that thing is there. The other question arises, who assigned the prefixes? Any idea? The prefixes, who is assigning these prefix when we are having the IP? Have you heard about this? Internet Corporation for Assigned Names and Numbers. They are top level authority basically, I'll say, who are coordinating the global IP addresses and domain names. And they are basically like for the global IP and all, global IP address and domain names, they are assigning it, and they are delegating this IP addresses to RIR, which is regional internet registries. So they are receiving a large blocks of IP addresses from ICANN, and they are allocating further to ISPs. I hope so. ISPs, you know, internet service provider. RIR, regional internet registries, they are allocating to ISPs, and ISPs basically they are assigning to business and end users, home users. I'd say. Is this flow clear? Like how these basically prefixes, IP addresses, basically these are assigned. Now coming to routing mainly. I'll not go to addressing and all as we have already covered that. So we have hop by hop packet forwarding. What does hop by hop means? Hop by hop means router basically don't know the path, full path. We have discussed earlier also that router don't know the full path from source to destination. What does they do? Instead, they forward the packet one hop at a time. So how this whole process is, let's try to understand in layman language. Packet is arriving at router. Okay. Router basically reads the destination address. What is the destination address? Okay. Checks now what is the next step? It will check the forwarding table, or I'll say lookup table, to find next hop. And then there is an interface. It will forward the packet through the interface, basically from where to forward, A, B, C path, which path basically to forward, which router basically to forward, next router what it should be, and then the next router will repeat the same process. In easy words, this is how it happens. So suppose you have to forward the data from your home PC to Germany, suppose. So router will forward to ISP, Internet Service Provider. Internet Service Provider will forward to regional hub, and then regional hub will forward to overseas, and then the packet will reach to Germany. This is how basically the step by step these things will this will basically happen. So that thing we have done that. Okay, we should have the hierarchical addressing and all, because obviously each host will have the unique, if it will have the unique IP, obviously we'll have huge memory usage, slow lookups, hard to update and all. So we should have hierarchical addressing and all, so that our address space we can our routing should be more easier to us. Now something there is longest prefix match. Before that, I'll come to CIDR. do suppose this is provider 1, service provider 1, and this is a provider 2. They both are containing this IP. So where the route should, like where the router should forward, any idea? Which one should choose? Which one we should choose? Which path we should choose?
Provider one.
Hmm? How?
Provider 201.10 more matching.
201.10 more matching. 20.
Actually, provider two's IP starts with one, or what's the
That
reference?
is what. No, no, no. I haven't written the IP. Basically, I was asking generally. Basically, longest prefix match. I'll say. I wasn't giving the example like though I have written here. Basically, it's like it depends on the how much match you are going through the same logic. Basically, how much match is there. Am I correct? That is
Yeah.
what you were thinking. I'll come to that, the longest prefix match. So how we'll decide a provider 1 or provider 2, that how much match basically, if it is both in provider 1 as well as in provider 2, we'll pick up the longest prefix there, I'll say. So whichever will be the longest prefix, it will go to that link. Suppose it's like provider 2 is like 201.1.0.6. Now can you tell? It's the same, I think. Sorry, sorry. Uh, okay. Suppose the IP address here is 201 dot. I have to go here. So which one I should prefer? Can you tell now?
Provider two,
Provider 2. Why provider 2?
more match.
More
Pref-
match. So more match, longest prefix match is there. Here also, here also we can go. Here also we can go. But we usually pick up the longest prefix match. Basically, longer prefix. That is what we usually do. But if I talk how we uh, how we are finding it longest prefix match, one algorithm is LPM algorithm, simple longest prefix match algorithm. You will keep the entry with the longest prefixes. Okay, this provider 1 is providing me. I can go to provider 1. Then you will go to provider 2. Then you'll match it. Then go to provider 3. Then you'll match it. But obviously, the router is having very few nanoseconds before the next packet is arriving. So we need something better rather than matching with each of the entry and all, hoping for the longest prefix match. So we better need some good data structure as well as algorithm. So that is why we have Petriasher tree. So it's like, suppose I'll give you a simple analogy. Imagine, suppose you are searching name in phone book. So earlier I was telling LPM algorithm simple. Instead of I'll say, you'll not check each and every name. What you'll check, first letter, second letter, and so on. And if the name doesn't share the common prefix, you will skip to the next thing. Basically, you'll check the first digit of your letter, second digit, and so on. That is how this tree works. You'll check the first one. Suppose it's like 0, 1, then 0, 0 again. You'll check where to go basically. Nodes are storing here the prefixes, and each bit is corresponding to the level in the tree. Is it fine? The way you check the in your phone phone book, the same way they have built up the tree with the prefixes and all. Though we can have faster lookups as well, like here it's like binary, we can have four array and all, four with four children, or those things also we can have. Is it clear? Should we proceed? So sorry. Wait a second. Should we proceed? Clear with this thing? Just like that, there is a tree maintained, a data structure maintained for longest prefix match. That's it, nothing else. So router needs a forwarding table, that we came to know. Okay, a forwarding table is there to send the packets. Now, how to populate that router? There are two ways basically. That is through first, right? Two ways to populate the forwarding table. One is static configuration.
Dynamic.
Yes, and the other is dynamic. Static. Can you tell about static? Admin is manually setting up, I can say, simple. But obviously network changes or there is a failure, so it's not that much visible. Static configuration. Dynamic router, it will adapt to link failures, network device, network failures, network changes and all. We have some dynamic protocols here which will help us in doing this like updating this routing table. We'll come to that. Okay, and if I talk about I want to forward the packet forwarding, how it happens by the end devices. So end devices like your laptop and all, obviously you'll not run any like the routing protocol there. How does it happen? If I talk about local traffic, let's skip this. I'll tell you what I'll tell you, Nisi. What does local traffic means? First of all, your computer to your printer, suppose you can deliver directly. LAN traffic via Ethernet. If I talk about external traffic, can I say we'll send to default gateway? What is default gateway? You might have heard this name default gateway many times. Any idea what is this default gateway? Yes.
It is the network address.
Are you sure?
Uh, I mean, it is used
Is
basically
it,
like that. This on what?
can I say it's a default router only? When I
Yeah,
want to communicate with the outside network, it's a default router.
the router's IP. That can be said.
Yes. So basically, default router's IP. When I want to communicate with the outside network, then I'll send it to this default gateway. So that is why external traffic, it is handled by the default gateway. That is what I'm trying to say. So packet delivery to the end, if I say, okay, this was the packet forwarding by the end host. If I say packet delivery to end host, obviously that is through MAC, through ARP, though that thing we have already discussed about that. Now, coming to routing algorithms and all, I'll come to them. Wait a second. Is it like, okay, I'll come to this, first of all, stability thing in routing. Is it like fastest path is always the stable path? Is there a relation between them? Any idea?
No.
Yes. Fastest path is always not the stable path. Sometimes we'll prefer stability over optimality, as we have also seen. Like there can be a fluctuating routes as well. So we have to take care of them. And also one thing, we'll come to this routing where we have I hope so these terminologies you are clear with: interdomain, intra-domain, global, decentralized. Inter means under the same admin. Inter means between the organization, different organization, between organization. Intra means within the organization. Global means you are having whole topology. You are having all the routers have complete topology, all the graph from source to destination, centralized one, I'd say. Decentralized means only the neighbors can are sharing. You don't have the whole topologies. You only know the neighbors only. You don't know the whole graph. Basically, I'm viewing the network as a graph here, so you don't know them. You only know the neighbors part. Is it clear? So, if I talk about next hop method, you know about next hop is basically when we are only here mentioning about in routing. We mention about what is basically our next hop. We don't mention the whole route here mostly. We mention about what is the next hop. This is the route method and this is the next hop method. If I talk about next hop method, obviously it's much faster, it's much scalable because we don't have to write the whole path, whole route. And here we have to write the whole route here. This is a whole route method. If I talk about host specific and as well as network specific, I'm telling about the types of the methods and which one we are preferring over the other. Host specific as well as network specific. Which one we'll prefer? Any idea? Yes, come on. Which one we'll prefer? Yes, yes. Am I audible?
Yes, ma'am.
Which one we'll prefer, host specific or network specific? Host specific means every host information is there, and network specific means the network information is there. Now only we have done, it's better to prefer the network specific because obviously if I'll write all the hosts which are in the table, if I am having a proper hierarchy of the network, and I'll prefer here, okay, N2 network, and the next hop is suppose R1. That's a better option rather than saying all the hosts, okay, A, B, C, D, what is the next hop and all. So obviously this is more scalable because less entries are there. So we prefer here network specific. Coming to the next terminology. default route. If there is no specific match in the routing table, what we uses the default route, which is often labeled as 0.0.0, which I'll say which points to the main router or default gateway. I don't know the in layman language what I'll say. I don't know the destination, send to main route or send it to default route. If I don't have any, if there is no specific match in the routing. Are these things clear? Should we proceed?
Yes.
Now we'll just check, as I haven't discussed that longest prefix match in more detail, like let's check that. Simple numerical, not numerical as well, simple thing. Suppose this is a destination. And network addresses. These three network addresses. We have prefix or mask, I'll say. And interface. Find the longest prefix match. How we'll do? Yes. Any idea? Wait a second. I'll have water and I'll come. Just in 2 minutes. Till that time, think about this. I'll come in 2 minutes. Yes. Am I audible? Yes. Any idea? Okay. Maybe we have done like that zeros and all, or the other part is first thing is the other thing I haven't. I have told you the numericals like append these zeros and all. You remember? M0. Yes, M0. Okay, I'll just show you the other thing also how we can do. What we'll do, we have the IP. We'll write the IP in binary. Okay, don't we this is the destination. We'll write 180.70.65.140 in binary. The other part is this mm, 26, which means we'll write a 250 network mask, which is subnet mask, I'll say 255.255.26 means how many ones are there in last octet? 2 ones are there and all zeros are there. Am I correct here? You got this? How 2 ones are there? Or should I tell you? Yes,
Yeah,
come on.
it's understood. 24 plus 2.
So 24 plus 2, that is 26. So if I'll say about the last, we'll see only last octet, because obviously this is now what we'll do. If I have to get the network address, what we do, we write the IP, destination IP in binary, we AND with subnet mask. This is one way. Other way I'll tell you. And we'll get the network address. So whatever the IP was there, so obviously if I'll AND it, I'll get the same result, because all these are ones only. So I'll only focus on the last octet only. So if I say 140, it's like 1 0 0 0 1 1 0 0, and here double 1 4 5 6. So this is basically 128. Am I doing something wrong? Is it correct? So this is the network address, I'll say. Okay. Though we are given with it. No, wasn't needed at all because it was given with us. Okay. Just for the information, if, okay, just a, if you want to know the network address, just for this, like you can have the IP and add it with the subnet mask, you'll get the network address. What is the other method? Okay, I'll not go with the question, just I'll tell you. Uh, just if we want to know. Okay, what is the other method? I think we have done in the class only. Any idea? Taking last bits of masking, the if I have 26, which means 6 bits are left, so I'll have those all those zeros there, which means I have this 140. 140 means, wait a second, 140 is this. So 10001100. I have this 140 and 26, which means I'll have 6 zeros here, and I'll get the network address. Though I'm telling you about the network address, here it's given to me. Is it fine? Yes. Is it fine? And how you got 26? Can you tell to the class? Can I say it's a longest prefix match? How it's a longest prefix match? Can I say here 180.70.65.128 to 26. 26, which means 2 power 6 host. 2 power 6 host means 64 addresses are there. Am I correct?
Yes, ma'am.
So 128, 64. Till 182 are there. Can I say this? Am I correct by saying this? And can I say it's the longest prefix? Because if I'll go to 25, then obviously, like, because here in 26 we'll have here two ones here. Here I'll go come to 1 1 here. So obviously this one will be the longest prefix which I'll prefer here. Are you getting the point, everyone? Am I making sense first thing? Yes. So how you have written M0? Can you tell to the class? Yes, Aman. To the longest prefix thing. Am I right?
Yes, longest prefix.
Oh, it's the easier way. Like obviously, this was the longest prefix. Though I went to that because though the network address was given there. So though you can think of if you want to get the network address, we can do this method as well as the zeros method. Though we have done, you can the zeros method we have done already. We have solved many questions regarding that. You can see them. Now one more way, the other way, one way is address aggregation. The technique I mean to say. What is this technique? Can someone tell me what is address aggregation and how it is helpful for us in the routing?
It involves creating hierarchies on subnets.
It's
So
basically, yes, yes, come on.
it helps in routing because if I have, let's say, 125 and 126, I can put a 20/24 above them, and then routing becomes easier.
Yes, yes, yes. So basically, I'll say in easy words, it's a process of combining multiple IP prefixes into single larger prefix. In easy words. So suppose I have 201.4.22.0.24 and 23.0.24 201.4. 24.0.24. So instead of basically storing separate entries, I can simply have 201.4.22.0 to 201.4.25.255 here. In the I can aggregate them instead of storing the same entries. We can have a one entry like this. So obviously, if the blocks are contiguous, then only I can have first thing. First condition is that only. The second thing is obviously I'll have the smaller routing table. Memory usage will not will be reduced there. It is easier to manage, I can say. So that is the advantage of address aggregation. Now coming to AS, autonomous system. Though we have discussed it, what is autonomous system? Basically, there is a single administrative domain, or I can say the collection of IP prefixes. They are under the single administrative domain. That is basically autonomous system. Or I can say that it is controlled by us, it is having the same common policy. And one more thing, we have the unique autonomous system number as well here. Coming to AS traffic now. Local, transit, stop, multi-home, transit. Okay, this is transit traffic. This is stub AS. I'll come to this. This is so. What is local traffic? I'm in this organization. I want to send the mail to the same organization. I'm in IIT Tirupati. I want to send the mail to the another user in IIT Tirupati. That is local. Transit traffic. that is passing through that autonomous system, but is not originating from them. Which means like AS from autonomous system 1, it is going to autonomous system 2, and then it is going to autonomous system 3. So this is a middleman there. That is basically transit. Stub, it is connected to only one autonomous system. So in, suppose in the small university, it is a small college, it is connected to Airtel, the internet. So that is stub AS. Multi-homed, they are connected to multiple autonomous systems. So if I have a large enterprise, suppose it's connected to Airtel as well as Jio. So if one fails, the other is there. So that is multi-home AS. So transit AS connected to multiple ASs and carries the transit traffic. That is basically transit AS. Is it clear? Should we proceed to routing protocols now? Clear?
Yes, ma'am.
So first thing is like we are having as intra-domain, inter-domain, it's cleared. I hope so. Intra within the organization, inter within different organization. Intra-domain, we have two types of routing protocol. That is distance vector as well as link state. And inter-domain, we have path. So coming to distance vector, in distance vector, what is, can someone tell me what is distance vector routing protocol? I'll come to an example as well. We'll solve an example also. Yes, come on. We'll solve the example of both distance vector as well as link state. What is distance vector routing?
It is somewhat like basically we create a kind of graph with costs and we pass multiple rounds where each router tries to find basically accesses the nearest router and updates its table. It is like Bellman Ford, something like that.
Yes, yes. It's basically uh, the main difference between link state and distance is basically distance vector routing is we are here here we are communicating with the neighbor only, with the neighboring router only. We are not communicating, we are not flooding the information to everyone, we are only communicating with the neighbor. And as you said, obviously it will be in the multiple rounds, we'll share our information to the neighbors in the multiple rounds. Let's see an example and try to understand it, like how we'll maintain the table and all. So let's take a simple example. I'll go to the next page as well. Have you received an email regarding Friday class?
No.
Okay. So though I have like filled the form regarding 2 hours of Friday class 6 to 8. Let's see. I haven't received the mail though. Most probably it will be on Friday. Let's see further. Like I'll try to cover the rest of the syllabus through questions and all, like through MCQs and all, so that everything should be covered. And in the last lecture, we'll have a revision, like on Tuesday. Hope so. We'll have the class on Friday as well. So let's see. So this is our suppose a network or a graph. I'll say for us a graph which is given to us. So everyone will maintain a routing table. So how these are the routers. This is the distance, or I'll say the cost or the distance. I'm not right because I have to make a table here. So everyone will maintain a table here. So first column of the table is the destination. The second column is the cost or the distance. And the third column is the next hop. So how much is the distance from A to A? Yes. 0. Next hop is A only. Am I correct? Making sense?
Yes.
What is the distance from A to B? 15. Next hop is B only. This is one edge. First of all, one edge distances. Like obviously A to C, there is no, I don't know because nothing has happened. This is initial routing table. So I'll mark as infinity and next hop, we don't know. From till D, it's 5 and next hop, it's D only. Similarly, let's update A, B, C and D. First of all, the first thing is obviously D is 0. D to A, that is 5. Next hop is A. And B, 8. Next hop is B only. C, 4. Next hop is C only. Can you tell me this one? A, infinity. B, 1. C, 0. D, 4. Similarly for this. A, 15. B, 0. C, 1. And D, 8. Till this point, is it clear? Yes, till this point, is it clear?
Yes, yes.
So this is the first part, first round, I'll say. Round 1. Local routing tables are there, and infinity means, I'll say, they are not immediate neighbors. Till this point, I'll say they are not till immediate neighbors, and this is only one edge distance here. One edge means there is a one edge between them. Now, what does happen? Now they'll share its distance vector. Everyone have their distance vector. Now they'll share their distance vector, share with their neighbors. So let's come to round 2. Now at A, so who will share with A? I'll say B and D will share with A. Am I correct? B will share the distance vector like table with the A. So B's table is 15, 0, 1, 8. D's table is 5, 5, 8, 4, 0. Now let us have the A table. Again, I'll update the A table based on this B and D. First thing is always A to A is 0. Now A to B. A to B directly is, I have A to B and the other thing is A to D plus D to B. A to B is 15. A to D is 5. D to B is 8. Which one is minimum?
13.
13. So I'll update is at 13. And through which path? I can say through D. The next hop is D. Similarly, A to C. The first part is I'll go from AB plus BC. The second is AD plus DC. I know AB, that is 15. 15 plus BC, that is 1. 15 plus 1 is 16. AD, that is 5. DC, that is 4. 5 plus 4 is 9. So which one is minimum? 9. Similarly, A to D, one is AD directly, other is AB plus BD. AD directly, it's 5, whereas AB, it's 15 plus BD, that is 8, that is 23. And minimum is obviously 5. So routing table of A is up. Is it clear? Is it clear? Yes, come on. Or should I go again?
Clear, clear.
So there is a shortcut also. If I'll say, though if you have a theoretical exam, obviously you have to do like this. There is a shortcut also. Suppose that A only. Let's see how. I mean to say this is the same thing only, just you don't have to do do this much of calculations and all. If it's MCQ type paper, what you have to do, again I'll write this 15018. This is shared with a 5840. This is shared with a, and I have to maintain the table of A. What is AB? I'll write here 15, and AD I'll write here 5. This one I'll write first. So AB is 15, and now what I'll do, I'll add up here. If I have to go to B, I'll add here. I'll add 15 plus 0, that is 15. 5 plus 8, that is 13. And 13 is minimum. I'll show you one more thing, one more example, then we'll come to it. Then C, I'll add 15 plus 1, that is 15. 5 plus 4, that is 9. So 9 is minimum. Here 15 plus 8, that is 23. 5 plus 0, that is 5. So 5 is simple. You got this? That was a long way. Like the same thing only. This is this. What I'm doing is, first of all, writing this 15 and 5, and then just adding 15 plus 0, 15 plus 1, 50, and comparing it with this one. So which one is the shortest? I'll write that. Is it clear? Does it make sense? The same answer you'll get. Is it clear? Or again, I'll tell you. Yes, come on. So the same way we can do with the others also. Any idea how many times we have to do before we'll get to the final answer? So basically we have to do, any idea? We have to again and again do. This is like first round, then we came to the second round. Again, there will be a third round and all. So we have to do it with the n minus 1 rounds. What is n here? N is the number of routers, which is suppose like here it's like 4 routers. So 4 minus 1. So 3 rounds we have to do. So as you can see, like A to B only. In the first round, we saw that it was 15. And then there was an edge added, like which was D. when I was going directly from A to B, and then when there was from A to D to B, I saw that it's 30. Now in third round again, an edge is added. Suppose I go through this way, that is A to D to C to B. Basically, rather than going from this, one more edge is added in round 3. So obviously it will like 5 plus 4 plus 1, that is 10. What is happening in each round, if we think intuitively, there is basically we are considering an increment of one edge every time. And as you can see here, with the increment of one edge, this A at least from distance from B, how it is basically getting reduced. Is it clear? Was this example useful for you guys? I mean to say, is the concept clear with this example? Yes. Should we proceed? Come on.
We can proceed, ma'am.
So basically, there can be a limitations as well, though I'll not go in that detail, like two node instability, three node instability. What does it mean? Like suppose there is a connection, there was a connection, but the connection is basically lost, and then there can be an instability within the network. Though I'm not going in that detail for that. Now coming to link state, let's solve the link state routing with the same example. As we have discussed that the link state routing is basically the flooding of the packets. So now here, again, I'll have a table here. Though here we don't have local routing table, here we are calling this as a link state packet. We are flooding it. It is not only shared with the neighbors. So it is shared with everyone. I'll say like earlier like B and D was sharing to A only. Here C is also sharing. That is why we are calling it as flooding. It is not only shared with the neighbors. Only local knowledge was not is not given here. Global knowledge is given as it is receiving from C as well. Like in the other case, it wasn't receiving from the C. I'll come to this sequence number and TTL afterwards. First of all, let's focus on this. A, D, as well as C, 15, 8, and 1. Similarly, C, sequence number. I'll come to the two rows basically. It's connected to D and B, 4 and 1. And here D, sequence number, TTL. It's connected to A, B, and C, 5, 8, and 4. A, sequence number, TTL. It is connected to B and D. And 5. So here what is happening? So link A, obviously, as I told you, suppose link A, earlier this is there. In the first place, we have this. Now what is happening? Link A will receive from info from B, C, D, not only from B and D, because it will receive a global knowledge, not only a local knowledge of its neighbors. So when it receives from B at A, suppose it receives from D first, it receives from D. Earlier it is having the information, okay, A it's connected with B and D. This it knows about it. Okay, this is okay. Now it refers D. When it refers D, it gets to know okay, D is connected with C and there is 4, and D is connected with B and it's like 8 here. It builds it. It refers D. Now again it refers C. C also floods the information. Everything else it knows, and then B to C it gets to know via C. Okay, there is a connection here. Wow. So then through it refers B table. Obviously by B table it knows everything. So the same information is there. Now it will apply a single so shortest path basically algorithm, that is Dijkstra's algorithm. Is it clear till this point? Should we proceed? So it's basically it will look directly that clear the extras by almost half. So it will now I have the whole topology. Basically, it will look directly okay. That A to A, which one is? I'll simply say A B C D. For A, I'll say first of all this is okay. 0. A to B, which is the smallest, I'll simply say here like 5 4 1. That is 10 through D. This path is the smallest. I have because A have the information about it. Then C, from A like A to C, I'll say this one is the smallest. 9 through D, and to D obviously direct is small. So by looking directly, I'll come to know. So unlike distance vector routing, I don't have to spend much time, much rounds here. It's the fastest method. I'll say it's a faster method than the distance vector routing. But sometimes there can be some problems in flooding. Let's see that. I'll come to this sequence number and all. That is what now I'm going to come. Now suppose R1, R2, R3, R4, and R5. So R1 directly transfers the packet to R5, and from this way, and from the other way it transfers like this. So obviously like this is flooding. R1 is transferring to everyone, flooding to everyone. So first time it floods, second time, third time, till the third time it's flooding the updated packet, and then the first time it's flooding from this way. When the packet number 1 is reaching the R5, this is suppose packet number 1, the first update, here the packet number 3 is reaching, means the latest information is reaching. Are you getting the point? Like here, suppose it's reaching very late, it's the old packet, it's the and this is the updated packet. Again, it has updated the table many times and it's reaching directly, it's going there, so it's reaching very soon. So I want to get to know like which one is the latest updated packet. So that's why I need the sequence number here. Like suppose R1, R2, R3, R4. This is R. This is the latest packet. So if one is received for like R1, I'll say, okay, I have the third updated packet. This you have sent it late. Like this is the first updated packet. This is 3 times it has basically updated it before only. So this is the old packet. So basically I can discard it. That is why we need this sequence number. And suppose, now I'll tell you why we need this time to live or timer basically. Suppose this packet, as we know, when we write the bits and all, there can be corruption in the bits as well. Suppose instead of 3, suppose it's by mistake written as 101. Obviously, when fourth packet will come, fifth packet will come, I'll basically discard them because I think I have 101th packet, which is a very updated packet. So I'll not basically receive these kind of packets till 102. I'll wait. But this is, but then there obviously it's a huge problem there. So that's why we have a timer. After some time, I'll discard these packets if they are not basically getting updated, and I'll accept the latest packet whichever is coming. And then what is time to live? This was timer and the sequence number to solve the problem. What is time to live? Yes, come on. What is time to live?
It is how long a packet will be alive after which it is cleared from the network.
So basically, if the packet is reaching within these hops, it's fine. Otherwise, the router will discard the packet. Can I say in other words? Is this problem clear? Like how, why the sequence number and all are there? Is it clear, or I should explain it again? Link state routing as well as this distance vector routing, are the examples cleared? Yes, come on. Come on. How was the class today? Was it interesting? The next part, I think path vector routing, BGP and all. We'll discuss basically. Okay, that may be okay. I was thinking to have the MCQs for the rest part so that we can cover the syllabus as well. And on the other hand side, we can discuss all those things as well. So the remaining part, I'll come up with the MCQs, though, or maybe I'll share in the drive beforehand only, or within the lecture we can see those MCQs and solve them. So that every part of every topic which is remaining, it should be covered on Friday itself. Any doubts? Anything which you want to share for Friday class or Tuesday class, next Tuesday or next Friday? Any feedback? Yes, come on. Concepts are clear. Routing protocols, mainly this distance vector and link state. Thank you, class. Let's meet on Friday. Most probably you'll get the mail, though I haven't also received any mail regarding that. I hope so. That is also 6 to 8 only. Okay, thank you, class.